we are learning about hybridization, and we have shown you the contours of sp hybrid orbital. Well, contours of other hybrid orbitals also look qualitatively the same, right. Quantitatively of course they will be different. Sp hybrid means, as you know, we have taken linear combination of a 2s orbital and a 2p orbital. Notionally we always take 2pz orbital, because generally if there is one bond we like to do it along z axis. But have a closer look at the contour diagram. So, what I did not discuss in the previous module is just have a look at these numbers. Here of course it is 0, right, this is the nodal surface. Then if you, let us start with the major lobe, this one is 0.1, these are all relative numbers, 0.2, 0.3, 0.4, and so here is the peak. This should not be difficult for you to understand, because we have actually plotted in real time those hydrogen atom orbitals earlier, and you have seen how these 3D shapes come and what contour lines are. And in the minor lobe, here I have shown the minor lobe to have a negative sign of a function. Here also, see, it is minus 0.4 outside, then slowly it comes in minus 0.1, minus 0.3. So, sorry, what am I saying? Minus 0.1 outside, minus 0.2, minus 0.3, minus 0.4 is in the middle, right. So, again it builds up on the other side, and the nucleus is engulfed by the minor lobe, and we talked about this, and then we said that if you look at the shape of 2s orbital, 3D shape, and 2p orbital, 3D plot, take sections, it becomes clear that in the immediate vicinity of the nucleus, it is a sign of the 2s orbital that takes precedence. And the interesting thing about 2s and 2p orbitals is that 2s orbital decays to 0 after a while with maximum at nucleus. 2pz is the other way around, it is 0 at nucleus, rises to a maximum later on. So, well, later on in terms of r, at longer values of r is more accurate. So, that is why in the immediate vicinity of the nucleus, it is the sign of the 2s orbital that predominates, and that sign does not predominate far away, because it is more than offset by the 2pz orbital sign at long distances from the nucleus, right. On one side you have constructive interference, that is where you get the major lobe, on the other side you get destructive interference, that is where the lobe becomes small. So, you can think that as a process of hybridization, what happens is, so what have we drawn? These orbitals, these are sort of, this tell you where the probability is more, right. If you think of a p orbital, if you think of an s orbital, it is it has no directionality. If you think of p orbital, equal probability this side, equal as that side, right, because okay, this side is minus, that side is plus in wave function, psi square dr or well deta, let us say, is the same, right. So, same probability, but we do not want that, we want the electron density to be on one side, so that the bond is highly directional, then we will get a strong bond. So, by formation of this major lobe and minor lobe, what we can effectively do is, we effectively ensure that we have a situation where the majority, most of the electron cloud is on one side, or rather we have prepared highly directional orbitals. Okay. Now, when I talk like this, of course I do not mean that we take acetylene and push the electron cloud, we do not. In acetylene, the electron cloud gets rearranged because it has to form each carbon has to form a bond with another carbon and a hydrogen atom, right. So, this is the driving force that ensures this rearrangement of electron cloud, that in a very qualitative manner you can say is hybridization. Okay, if you want to think of it without invoking even the little bit of math that we are doing. Okay. Everything, if you remember the discussion we made of Pauling's introduction to this, it is a field that determines what kind of hybridization there will be. Here the presence of other atoms, that is the driving force, how many bonds are to be formed, that leads to a redistribution of electron clouds, which in other words is formation of hybrid orbitals. Okay. So, we have talked about sp orbitals. Now, it is time to talk about some other geometry. Sp orbitals are good for linear geometry. Now, we want to talk about the next step, Linear geometry means Ab2 kind of molecules, triatomic molecules. Of course, acetylene is not triatomic, but let us keep things simple. Next I want to talk about Ab3 kind of molecules, that is trigonal geometry. Since I need 3 hybrid orbitals like this and they have to be at 120 degrees with each other, I need 3 atomic orbitals to participate in the process of hybridization. Now the orbitals that I use are s and p orbitals, right. 3 orbitals, one has to be s always, right. You cannot really mix only 3 p orbitals and get what you want. Okay. You mix 3 p orbitals, you will never get 3 orbitals in a plane hybrid orbital, that is why s is required. So s and 2 p orbitals. So let us work with for now px and py orbitals, and let us say that these hybrid orbitals are in some orientation. So the angle with x of hybrid 1 is theta 1, the angle with x for hybrid 2 is theta 2, and for hybrid 3 the angle with x is theta 3. Please remember, I have only defined angles with x axis. So now if I want to write an expression of these orbitals, right, what will the wave functions be? The wave functions will be something like, so let us say I want to write, I will write psi 1, okay, for hybrid 1 I am writing psi 1, and please do not worry if you cannot read my handwriting, in any case everything is written nicely down below. That is equal to, say, some coefficient C1 multiplied by psi 2s plus some coefficient multiplied by psi 2px plus some coefficient, let us say, multiplied by psi 2py. I do not need psi 2pz, right, because I am working in the xy plane. So px and py are the orbitals that I should use. So I have held the molecule in the xy plane for my convenience. In ideal case scenario it should be held with any orientation in space, right, but I want to simplify the problem, so I am putting it like this, and we will come back to this several times in our discussion. So now see, can I not write something like this? C1 is fine, instead of C2 I can write C2 dashed multiplied by this. In place of C2, will you disagree if I write C2 dash multiplied by cos theta 1 psi px, and this will be not C3, C3 is going to be the same C2 dashed sin theta 1 psi px. That way we have a little bit of a control over the system, right, because what these cos and sin tell us is sort of the components. We are working out components, these are like vectors, right. These arrows that I have drawn, these are the hybrid orbitals. You can think of this arrow as one hybrid orbital, you can think of an arrow here as px and an arrow here as py. So like we resolve vectors into the components, I can write like this, then it becomes a little easier because you know what, this has to be normalized also. So the C1 dash can go out in the normalization constant. What about C1? We will see. So we will write like this. Here I am not even trying to normalize yet, actually there should be a normalization constant multiplying this. These C1s, see what we have written same C1 for psi s everywhere. Why? Because the contribution of s to all the orbitals has to be same, we are working with the with equivalent orbitals. So s character is same. Also there is only one 2s orbital in the atom. So there is, I hope it is not very difficult for you if I write 3 C1 square is equal to 1, because see C1 square is contribution of this s orbital in the first wave function, C2 square is the contribution of psi 2s in the second wave function, second hybrid wave function. This, well, again this is C1 square is the contribution of psi 2s in the third hybrid wave function. So, the total contribution has to be 1 because there is one 2s orbital. So, 3 C1 square equal to 1. So, C1 is equal to 1 by root 3. This is something we are going to use later also. So, already without much hassle I have found out C1, and what I can also do is, if I know what theta is, actually I do not have to do anything. I just write the value of cos theta 1, I will write the value of sin theta 1, theta 2, sin theta 2, sin theta 3, cos theta 3, and I have got the hybrid wave functions. Then if required I can normalize. Okay. So, this is the most general strategy of writing expressions for your hybrid orbitals. But what we will do is, see, we have simplified the problem here by holding it in xy plane. So, since we are willing to do that, why not simplify it even further by holding one of the hybrid orbitals along one of the axes. That will make life even simpler, right. So, this is how we are going to work out the actual coefficients for this problem. You might get a little baffled here and you might think, what is going on? Who has told you that one of the hybrid orbitals is along y axis? Nobody has told me, but nobody has told me where y axis is, right. It is in my hand. We are working in free space, we are pretending as if we have this one molecule and nothing else. So, I can set my axis in whichever way I want. If you have objections to me playing around with the molecule, then I will play around with the axis, right. If Muhammad does not go to the mountain, well, mountain will go to Muhammad. It is not so difficult, it is relative motion. So, let us say that we work in a situation where the first hybrid orbital is aligned with the y axis. The advantage of doing this is that your coefficient of this Py is going to become 0 for the first hybrid orbital. So, C3 will be 0. First of all, I have written a general expression for the hybrid orbital. So, what I am doing here is that I am writing phi for hybrid orbital wave functions. I am writing phi for hybrid wave functions, I am writing psi for the pure atomic orbitals. So, for H1 I have written C1 psi s plus C2 psi px plus C3 psi py. For the second hybrid I have written C4 psi s plus C5 psi px plus C6 psi py. For third one I have written C7 psi s plus C8 psi px plus C9 psi py. I have just given numbers to coefficients. You are free to use different notations. You can want to write C11, C12, C13, or you want to write C1s, C1px, C1py. Different books use different notations. Please write whatever you want. I have used a simple notation in which we give the simple tags to the coefficients. Okay. Now, how can we simplify this? But before that, let us look at the picture once. I have held the molecule in xy plane, I have held H1 along y axis. So, naturally the second hybrid is going to be like this. Let us say the second hybrid is towards the positive side of x and negative side of y. The angle between y axis and H2 is 120 degrees, angle between y and x is 90 degrees. So, this angle between x and H2 is 30 degrees. Similarly, the angle between x and H3 is 30 degrees and H3 has to be on the other side. So, minus x and minus y. I hope that is not difficult to understand. Now, let me try to write the coefficients one by one. So, we have written phi h1 sp2 to be retained C1 from here, C1 psi s plus, as we had said earlier, there is no contribution from Px here because the orbital is aligned with H1. Is there a contribution from psi s? Definitely, otherwise this shape will not change, right. So, no contribution from Px and a contribution from C3. So, one s orbital and one p orbital are contributing. Does that make it an sp orbital? No, it does not. It is still sp2 orbital. Please hold on to this thought and we will come back to it. Okay. Now, do we know what the C1 is? Actually we do. Remember, the C1 must be equal to C4 must be equal to C7, remember, because s orbital has to make equal contribution to all the hybrid orbitals. So, C1 must be equal to C4 equal to C7. So, 3 C1 square must be equal to 1 as we have discussed earlier. C1 is actually 1 by root 3. So, you already know 2 of the coefficients. C1 is 1 by root 3, C2 is 0. Can we figure out C3? Well, I have done it in a particular way on the slides, but let us just go by whatever we are discussing. So, this is 1 by root 3 C1, C2 equal to 0, and we know that for normalization C1 square plus C2 square plus C3 square must be equal to 0. So, 1 by 3 plus C3 square is equal to 0. What am I doing? I am as usual making a mess. If it is 0, then that is the end of it, is not it? Physical chemists are sometimes obsessed with zeros, but they are also obsessed with 1. We are talking about normalization condition, remember, right? We are talking about normalization condition. Which means your integral phi h1 sp2 phi h1 sp2, that has to be equal to 1, which means I will write it here and then I will erase integral C1 psi s, put a bracket here, plus, okay, I will not even write this because you are already convinced that this is 0, plus C3 psi py, and the same thing C1 psi s plus C3 psi py, that is equal to 1. If you expand this, what do you get? You get C1 square integral psi s into psi s over all space. What is this? This is equal to 1 because psi s is normalized. Similarly, I can get C3 square, again I will get psi py into psi py integral whole square, plus I write C1 C3 integral psi s psi py, that is going to be equal to 0, right, because this s and p are orthogonal to each other. Similarly, the last term will also be equal to 0. So, C1 square plus C3 square will be equal to 1. So, 1/3 plus C3 square equal to 1. So, C3 is equal to 1 minus 1/3 is 2/3 root over 2 by 3. Not very difficult to figure, in fact it is very easy to figure out. I do not even have to do the rest, you can, I think, figure out the rest by yourself. It is very simple, fun, like this is like solving Sudoku or something, and it gives you some very interesting insight. Okay. Hold on to the thought, the question that we had raised, that in the first orbital we are mixing your one s orbital and one p orbital. So, is that sp hybridization? And we said no, the hybridization is still sp2. How did that happen? Actually, I have answered the question already, but I have not told you that. We will come to the answer, but by then see if you can figure it out yourself. See if you can convince yourself that it is really sp2 and not sp. Okay. Meanwhile, we will go ahead and we will write the expression for psi h2. So, psi h2 I can write as, we will keep C4, there is no need, I already know that it is 1 by root 3 plus C5. Here I will explicitly write minus C6 because I know very well that psi 2 is on the negative side of y. So, the value of Py, the value of coefficient of Py has to be negative. So, what I will do is I will keep the coefficients, the C's, not coefficients, the C's, Cy, C1, C2, C3, I will keep them to be either 0 or positive. So, I will write the sign explicitly, that will be minus. And if I want to write an expression for psi h3, will you agree with me that it has to be C7 psi s with C7 equal to C1 equal to C4 equal to 1 by root 3, C7 psi s minus C8 psi px minus C9 psi py. Will you agree with me? Because this h3 is towards minus x as well as minus y. So, both the coefficients should have explicit minus sign. Okay. Now, how do we go about it? How do we work this out? now we remember the angle. The angle is 120 degrees. So, this angle between x and H2 is 30 degrees. This angle between minus x and H3 is also 30 degrees. This we have done already. This is total x contribution is 1. See, what happens is when we prepare the slide, we have some particular kind of chain of thought. By the time I come and I speak here in front of you or in front of the camera, the chain of thought sometimes evolves. So, I might not be saying things exactly in the same sequence, but everything is there. So, we have already figured this out. Okay. This is important. This is something I have not said. See, mod C5 is equal to mod C8. Do you agree? Mod C6 equal to mod C9. Mod C8 equal to mod C9. Do you agree? Here I have already written C5, unfortunately. So, what I am saying is modulus of the coefficient. So, well, there is no need to write modulus also, because I have made the coefficients the C's, I have made them positive already. So, mod of coefficient of psi px has to be the same for H2 as well as H3, because the angle is 30 degrees, right. So, what will this component be? They should be the same in magnitude. So, I will write this as C5, I will write this as minus C5. Similarly, this will be minus C6, this will be minus C6. What else can we write? We can write all these things. C1 square plus 0 plus C3 square equals to 0, we already did that. C1 square plus C3 square, C5 square plus C6 square equal to 1. That is again from normalization condition, you will get the same equation from H2 as well as H3. So, for Px and Py coefficient, 0 plus C5 square plus C5 square equal to 1. This is C5, this is C5, this is 0. Okay. Now, we are almost done, right, because once again, how many px orbitals are there? This is one px orbital, right. That is why we are saying that this C5, where is it gone? 0 plus C5 square plus C5 square equal to 1, 0, C5, C5, and when I take square, this minus square of minus becomes plus also. So, I do not remember where the white space is, I will write here. So, what do I get here? 2 C5 square equal to 1. So, C5 is equal to 1 by root 2. I hope you have your pen and paper with you. Please write these values down, because I have everything written down in the next slide, but if you write down you can check. So, 1 by root 2, that is what I have got. So, how many coefficients are left now? Out of the 9 coefficients, we have figured out all these. Oh, I need the pen. We have figured out these, we have figured out this, we have figured out C5s also, we have figured out C3. The only thing that we now want to find out would be C6. Okay. How do I find C6? Is it difficult? It is not difficult, it is very easy, right. Because now you can use anything, you can use normalization condition by taking C1 square plus C5 square plus C6 square equal to 1, or you can use orthogonality also. You can say this C1 square plus 0 plus C3 into C6 equal to 0. So, you already know C3, so only unknown will be C6 and you can find it out, right. So, when you do that, this is what you get. I hope the coefficients we worked out are all matching. 1 by root 3, root over 2 by 3, 1 by root 2, these we worked out, these come out to be 1 by root 6. Okay. So, very nicely we have been able to figure out the coefficients of the atomic orbitals in the hybrid orbitals, hybrid sp2 orbitals, when we hold the molecule in xy plane with one of the hybrid orbitals along the y axis. We have found the coefficients and we have written the expressions. And first thing we see is they are all orthogonal to each other. They are normalized. We have used the normalization condition. Are they orthogonal? It is easy to see H1 and H2 or H1 and H3. 1 by root 3 into 1 by root 3 is 1 by 3. Then root 2 by 3 into minus 1 by root 6 is equal to what? Root 2 by root 3 is equal to again 1 by 3. So, plus 1 by 3, and here we are multiplying plus by minus, so it is minus 1 by 3, that is equal to 0. So, please satisfy yourself that how many pairs can you take? 3C2, right, factorial 3 by factorial 2, 3 pairs. All the 3 pairs of these H orbitals, hybrid orbitals, they are orthogonal to each other. Please convince yourselves, please work them out. Please also convince yourselves that they are normalized, but it is not even required because we have used normalization condition to even construct them. Now we come back to that question. The first one, is it sp2 or is it sp? Well, to answer the question, we need to remember that the mod square of any coefficient gives us the contribution. So, in the first orbital, contribution of psi s is 1/3, or you can write 0.33 if you want. I like 1/3 better. Contribution of py is square of root 2 by 3, well, 2/3. What is the ratio of how do I write it? S character, I write like this, is to P character. Oh man, such bad handwriting. The ratio of S character to P character is 1 by 3 is to 2 by 3 is 1 by 2. So, sp2. sp2 means contribution of S in that orbital is 1/3, total contribution of P is 2/3. I should not have said that now because that is a little bit of a spoiler for what I am going to say after this, but it is okay. So, contribution from p orbital has to be twice the contribution of s orbital. That is the meaning of sp2. It does not mean that exactly one s orbital has to mix with exactly 2 p orbital. We are dealing with wave functions here. So, scaling, remember scaling, the scaling and all can be done. Let us look at H2. What is the contribution of s orbital? That is a foolish question now because contribution is same, 1/3. What is the contribution of psi px? It is actually half. What is the contribution of py? It is actually 1/6. So, what we see is that px contributes to a lesser extent to H2 than does py, and that is not so surprising, right, not so surprising also. Sorry, what I was saying, px contributes to a greater extent than py. This is half and this is 1 by 6. That is not so surprising, just look at this figure. This angle is 30 degrees, this angle is 60 degrees. It is no wonder that the contribution of px is going to be 3 times more than contribution of py, right. Look at the components, you will get it. But what is the total contribution of p orbitals? Half plus 1/6 is equal to, since it is easy, I will actually do it in detail, is equal to 4 by 6 is equal to 2 by 3. Total contribution of p orbitals is 2 by 3, same as what it was in H1, right. So, total contribution is the same, and it is not very difficult to see that total contribution of P once again here is 2 by 3 as compared to 1 by 3 for S. So, all are sp2 hybrid orbitals, all are equivalent, and meaning of sp2 then is what is the contribution, that contribution of S is 1/3, total contribution of P, total P character is double of that, 2/3, 0.33 and 0.67 if you will, right. So, this is what we have worked out. From square of coefficients we have established that contribution of S is 0.33, contribution of P I should write 0.67 in all the orbitals, they are all equivalent, and using them you can now perform bonding in the familiar way for these molecules that are familiar to all of us. So much for your sp2 orbitals. Well, we started in a way that the angle is 120 degrees, but our time is running out, so we will stop now, but a little bit of this discussion of sp2 orbitals is left for the next class. We will do back calculation like what we did earlier remember when we were testing our approximate methods, we worked with systems for which exact solution was known and we tried to see whether we get the result. We are going to calculate the angle and see whether we get 120 degrees. That is going to be very useful for us when we talk about sp3 orbitals later on. But let us take that along with sp3 orbitals in the next class.